Welcome to Deep Dive with Phil and Emily.
Hi, everyone.
Today we're diving into the world of statistics with Professor Wu to help us along.
Yeah.
And we're going to be looking at expectation and variance.
We're very important concepts.
Yeah, super important concepts that can really help us make sense of data and make predictions.
Absolutely. It's fascinating how these concepts actually underpin so much of what we do.
Yeah.
I mean, from understanding averages to, making those informed decisions that we have to make every day.
So Professor Wu starts by talking about the average height of the U.S. population.
Okay.
Which he says is 5 feet 5 inches.
Right.
And he explains that, typically we calculate this by adding up everybody's height and then dividing by the total number of people.
That's right.
But then he introduces this whole other way of looking at it, the probabilistic perspective.
Right.
What is that?
Well, the probabilistic perspective really kind of shifts our focus from just the data itself to the probabilities of different events occurring.
Okay.
So instead of just looking at everyone's height, we start thinking about the chances of someone being a certain height.
Okay.
So it's not just about the average, but also the likelihood of different outcomes.
Yeah.
And that's really where expectation comes in.
Okay.
It's also known as the mean right.
Yeah.
And it represents the most likely outcome.
Got it.
The value we'd expect to see most often.
Okay.
So Professor Wu mentioned that expectation is the summation of x times p of x.
Right.
Can you break that down a little bit?
Yeah, what is that?
Well, think of it like this. So x represents each possible value.
Okay.
Like different heights, right?
Uh-huh.
And p of x is the probability of that value occurring.
Got it.
So we multiply each value by its probability
Okay.
and add those products together.
Right.
It's like a weighted average where the probabilities are the weights.
So the more likely a value is, the more it contributes to the overall expectation.
Exactly.
Okay, that makes sense.
Yeah.
Professor Wu also mentioned that we don't need everyone's height to get a good estimate of the average.
Yeah, you don't need the entire population.
We can use a smaller sample.
That's right.
How does that work?
Well, that's the beauty of the law of large numbers.
Okay.
As our sample size grows, the difference between our sample average and the true population average shrinks.
Okay.
It's like magic. A carefully chosen subset can actually represent the whole.
That's pretty reassuring.
Yeah.
But even within a sample, not everyone is the same height.
Right.
There's variability. How do we capture that?
That's where variance comes in.
Okay.
It measures the spread of data around the mean.
Okay.
Essentially the average distance from the center squared.
Okay, why do we square the distance?
Well, squaring ensures that we're only dealing with positive values, right?
Right.
Otherwise, the negative and positive differences from the mean could cancel each other out.
Okay.
And that would give us a misleading picture of the spread.
So a larger variance means the data is more spread out, and a smaller variance means it's more clustered around the mean.
Exactly. Imagine two groups of people.
Yeah.
In one group, everyone's height is pretty close to the average, right?
Right.
And in the other group, you have people who are much taller and much shorter than the average.
Right.
That second group would have a larger variance.
Okay, that helps me visualize it. But how do we actually calculate variance?
It's not as scary as it sounds. We take each data point,
Okay.
figure out how far it is from the mean, square that distance,
Okay.
and then average all those squared distances.
So we're essentially finding the average squared deviation from the mean.
You got it.
I get it. But squaring the distances seems to make the result a bit abstract.
Right.
Is there a way to make it more intuitive?
Yeah, that's where standard deviation comes in handy.
Okay.
It's simply the square root of the variance.
Okay.
Bringing us back to the original units and giving us a more tangible measure of spread.
So the standard deviation tells us the average distance of data points from the mean.
Precisely. And here's a helpful rule of thumb. About 68% of the data typically falls within one standard deviation of the mean.
Okay.
And about 95% falls within two standard deviations.
Those are some handy benchmarks.
Yeah.
So if we know the mean and standard deviation, we can quickly get a sense of how the data is distributed.
Exactly.
Professor Wu also mentioned two different ways of calculating variance, one for the entire population and one for a sample. Why the distinction?
Well, the difference really lies in how much information we have.
Right.
When we're dealing with the entire population, we know the true mean.
Right.
But with a sample, we only have an estimate of the mean, which introduces a bit of uncertainty.
So using the same formula for both scenarios could lead to a slightly inaccurate estimate of variance for a sample?
That's right. To account for this uncertainty, we use a slightly modified formula for sample variance, dividing by n-1 instead of n, where n is the sample size. This adjustment helps us get a more accurate estimate of the population variance from our sample.
It's like a subtle tweak to compensate for the lack of complete information. Clever. Professor Wu emphasized that both variance formulas essentially capture the same fundamental idea, the average squared distance of data points from the mean.
Exactly. And that idea is at the heart of understanding how spread out our data is. But as you pointed out earlier, squaring the distances can make it a bit hard to grasp the practical implications. That's why we often use standard deviation, which brings us back to the original units and gives us a more intuitive sense of the average distance from the mean.
Professor Wu also touched on this concept of functions of expectation. It sounds a bit intimidating. What's that all about?
Sometimes we're not interested in the expected value of the data itself, but rather the expected value of some function of the data.
Okay.
Imagine we're not just interested in the average height of a population, but the average squared height.
Why would we ever want to do that?
It might seem odd, but there are cases where this concept is really useful, for example, in finance. We might want to calculate the average return of an investment, but the return itself could be a complex function of factors like interest rates, market volatility, and so on. By understanding functions of expectation, we can calculate the expected value of this complex function directly.
So we're essentially taking the expectation of the transformed data. That's pretty powerful. But are there any limitations to these statistical measures? Do they always tell the whole story?
That's a great question. Statistical measures are incredibly useful, but they are just tools. They can summarize data and highlight important patterns, but they don't always capture every nuance of real-world phenomena.
So we should be wary of relying solely on these numbers.
Exactly. It's crucial to remember that statistical measures are based on certain assumptions and can be influenced by outliers or skewed data distributions. We should always complement our statistical analysis with visual exploration of the data domain expertise and critical thinking.
It's a reminder that numbers can be both illuminating and misleading. Professor Wu also discussed the idea of bias and variance in the context of model selection, using the analogy of target shooting. Can you walk us through that?
Imagine you're aiming at a target if your shots are consistently clustered together, but off-center, that's high bias. You're systematically missing the bullseye.
Okay.
On the other hand, if your shots are scattered all over the target, that's high variance, you're hitting different spots, but not consistently.
So ideally we want low bias and low variance, hitting the bullseye consistently.
Exactly. But achieving that balance can be tricky. A simple model, like a straight line, might have high bias because it can't capture complex patterns in the data, but a complex model might overfit the data, leading to high variance.
It sounds like we need to find the Goldilocks model. Not too simple, not too complex. Just right. How do we do that?
That's where model selection comes in, and Professor Wu recommends splitting the data into 3 parts: training, validation, and test sets.
Why is that so important?
It helps us avoid bias in our evaluation. We use the training data to teach our model the validation data to choose the best model among several candidates, and finally the test data to estimate the chosen model's performance on unseen data.
So we're essentially creating a more realistic scenario for evaluating our models. It's like a baking competition. We train our bakers with different recipes, have them try out their skills in a practice round, and then have the final judging.
That's a great analogy, and this approach called train, test, validate, split is the gold standard for model selection in data science today. Professor Wu shared a fascinating example of how these concepts are being used in a very unexpected area, assessing babies' neurological development.
Really, tell me more.
Researchers are studying babies' pacifier sucking patterns.
Oh, wow.
Because babies can't talk. These patterns offer valuable insights into their development by collecting data on babies' age and sucking behavior. They can build models to predict a baby's age based on their sucking patterns.
That's incredible. Who would have thought that something as simple as pacifier sucking could reveal so much about brain development?
It's a testament to the power of these statistical tools, and it highlights how these seemingly abstract concepts have real-world applications that can impact lives in meaningful ways.
It seems like Professor Wu has given us a powerful toolkit for understanding and navigating the world of data.
Absolutely. And as we gather more data and develop more sophisticated computational tools, our ability to extract meaningful insights from that data will only continue to grow. It's an exciting time to be exploring the world of statistics.
Yeah, it's amazing how these fundamental statistical concepts, have such wide-ranging applications.
Yeah, it really speaks to the power of data analysis. By understanding these tools, we can unlock a deeper understanding of the world around us.
Yep.
I mean, from predicting market trends to, assessing those developmental milestones in infants.
But with so much data being thrown at us these days, it's easy to feel overwhelmed.
Right.
How can we, as non-statisticians navigate this data-driven world?
That's a great question. And, it's more important than ever to be informed consumers of data. When we encounter statistics, whether in news articles, scientific studies, or even social media posts, we need to ask critical questions.
What kind of questions should we be asking?
Well, we should ask ourselves, what do these numbers actually mean?
Okay.
What are the assumptions behind them?
Right.
Are there any potential biases, in the way the data was collected or presented?
Yeah.
And what might be missing from the picture?
So it's not just about accepting numbers at face value.
No.
We need to approach them with a healthy dose of skepticism and critical thinking.
Absolutely. It's about developing a discerning eye that can see both the power and the limitations of statistical analysis.
Yeah.
Numbers can be incredibly illuminating, but they can also be misleading if we don't understand the context.
That's a great takeaway. It's like Professor Wu said, statistics isn't just a dry academic subject.
Yeah.
It's a vibrant field with real-world implications, that touch all aspects of our lives.
Absolutely.
And as our world becomes increasingly data-driven, understanding these fundamental concepts will become even more crucial.
For sure.
Well, thanks for guiding us through this deep dive.
You got it.
It's been an eye-opening journey.
It's been my pleasure. Remember, statistics is a powerful tool for understanding the world around us.
Yeah.
But it's up to us to use it wisely and responsibly.
Well said. That's our deep dive on expectation and variance.
Thanks for joining us.
Thanks for joining us.